Good afternoon. My name is Jesse Coro, Director of North America Operations at ERLab. For those who don't know, ERLab provides exposure control solutions. Who here in the audience has heard of ERLab or has products of ours? Excellent. Some do, some don't. Well, for those who don't know, we are the global leader in air filtration solutions and have been providing these solutions since 1968. All the products you see on my screen here today represents products that eliminate the exposure risks and protect the breathing zone of lab technicians. All of our products are independent from the building's infrastructure. Therefore, they're sustainable and they increase safety within the laboratory. Today, specifically, our agenda is going to be talking about bridging the gap between compliance and safety. And we're going to talk about OELs, occupational exposure levels, and should these standards really determine whether or not the lab is safe. Of course, we're going to talk about the holistic options with the power of filtration and how they can integrate into your laboratory, therefore providing a safer environment. And of course, I want to talk about safety standards of filtration, specifically ductless fume hoods, because there probably are some misconceptions regarding the safety and the effectiveness of this technology, which I'm going to touch on. And of course, I'll leave the end of this presentation open for any questions and answers. So let's start with OELs. What is safe? Well, as you see, there is discrepancies between OSHA, NIOSH, and ACGIH as to what is determined to be safe. Now, for those who don't know, many of you do, the TWA, the time-weighted average, is the average amount of concentration that we can be exposed to throughout a 40-hour working week for over 40 years. Now, with these discrepancies, I would not want to be exposed to any of these. And we see some of these chemicals like hexane where OSHA allows 500 ppm, but NIOSH and ACGIH allow only 50 ppm. Again, what are the standards in which we consider to be safe? We must go beyond compliance. To us, any level of exposure is too great. The cumulative effects of this exposure wreaks havoc on our system and can cut our lifespan short. So again, we want to address these issues within the laboratory and do better, provide safer solutions so that we improve the longevity and the life of those working within our laboratory. We all know the risks of exposure. I talked about those a moment ago, but we really think about the short-term exposure risks: headaches, coughing, breathing, skin irritation, sore throats, eye irritation, all those things I'm sure you have all experienced, or have some of your employees saying, hey, I think I'm overexposed. I'm getting issues consistently with my eyes. I have headaches. I have throat irritation. All this happens within the laboratory, but we don't really think about the long-term effects. These long-term effects wreak havoc on our system. Respiratory disease, impacts on our liver and cardiovascular disease, and even can affect our central nervous system. So again, we should not consider, I'm going to move to the previous slide, these exposures acceptable. We must go beyond compliance, and you can just see some of the risks of exposure here just from toluene and hexane. The risks are significant. So why do we allow ourselves to have this continuous exposure of these emissions? I don't believe we should follow these guidelines to a T. We must do better. We must improve, and we must develop our own standards to ensure the safety of those working within the laboratory. So the next slide is really about exposure and the numbers and diving deeper into why we do what we do. So I'm going to throw some numbers up on the screen. And if anybody knows what these numbers represent, please do raise your hand and let me know. Let's have some fun with this. So the first number, 480. Anybody in the audience tell me what this number represents? Yep, I heard it. It's the average minutes we are in a lab per day, 480 minutes. 3,840. Does anybody know what this represents? It's the liters of air we breathe while at work, which is equivalent to 1,000 gallons of air that we breathe at work every single day. This is a 1,000-gallon watering truck. None of us would deliberately ingest this water if we knew it was polluted. We have a choice, however. We have filtered water. We had fresh spring water. We take very good care of what we intake as far as what we drink. We would not drink polluted water. Unfortunately, with air, we can't see the majority of pollution. Now, of course, we could see wild smoke and things of that nature, yes, but the majority of exposure risks we cannot visualize. Therefore, it's out of sight, out of mind. So we must, again, address the air we breathe. And this goes into my IAQ webinars that I present. We don't always think about the air we breathe. Again, it's essential. We don't breathe, we die. So what's the choice? The choice is provide better protection, and that's what we must do. So this equates to over 5,000 gallons of air that we breathe every week while at work, and over 250,000 gallons of air that we breathe every single year. Allow that to resonate for a moment. That's what we're breathing. Now, our bodies are filters to some extent, but we're pushing the limits. Again, why it is so important to go beyond compliance. So what should we do? Well, improve safety within the workplace to mitigate the risk of harmful emissions, both inside and out. And I say inside and out because a lot of times we all know we use ducted hoods as one of our engineered control systems. Well, these ducted hoods release pollution out into the atmosphere. That pollution is then re-entrained into some buildings, some building that may even be adjacent to that very same laboratory, or re-entrain these emissions back into the very same building you're trying to dump them out of. So with filtration, we're capturing at the source, and we're not allowing these emissions to be thrown out into the atmosphere. And we have the safety standards to ensure we're not allowing high concentration levels of pollution back into the lab. And I'm going to touch on that in a moment. We must develop an IAQ risk assessment, no exposure levels, and aim to reduce exposure below TWAs, please below TWAs. Establish your own OELs based around your overall risk management policies and stay in the loop to new OELs under the TSCA. It's critical. And apply proper administrative and engineering controls, which we all do, and we do our best job at it for what we know, but we can improve. This just represents how a lab can be outfitted with a complete line of filtered solutions. Again, at source containment, developing solutions for storage of your chemicals, solutions that go onto a flammable or acid cabinet, because these become the most noxious and hazardous cabinets within the laboratory, releasing high concentrations of pollution when these doors are opened, and then whole room air filtration systems capturing fugitive emissions consistently so that we don't have high loads or we don't have that risk factor at the TWAs, reducing concentration. We all know engineered control solutions, and I mentioned those a moment, but today we're specifically talking about those engineered controls, which are fume hoods, chemical fume hoods, powder weighing stations. We all know biosafety cabinets are an engineered control device, downdraft tables, chemical storage. But we're going to really dive deep into the details and peel back the layers a little bit on fume hoods, specifically ductless filtering fume hoods. Traditionally, again, as I mentioned earlier, we take air from our fume hoods that's ducted out into the environment and we throw that air out into the atmosphere. There's a lot wrong with this. Now, there is a need for ducted fume hoods, and my intent here is not to say there is not a need for ducted fume hoods, but because there is. And we do have limitations with ductless technology. I'm going to touch on that in a moment also. But what I'm saying is, every time we add a hood or every time we design a lab or renovate a lab, it doesn't all have to be ducted because there's serious consequences involved with this. They consume massive amounts of air, starving your air handling units, reducing the air needed for proper dilution. Because then you need a bigger air handler, and sometimes you can't achieve the proper air exchange rates necessary because you're starving it. You're starving the system. The cost of air, not many people associate air as cost, but the cost of air has increased by 54% since 2006. And you can see the trends year after year after year. Of course, we saw significant spikes in 21 and 22 and now in 23. I talked about re-entrainment of pollutants back into your laboratory. You look at this diagram down here. Yes, while it's a little bit comical, the reality is we are throwing and dumping these pollutants back into the atmosphere. And people walking down the streets, I'm from Boston, if you can't tell from my accent, I walk down the streets of Boston or Cambridge, there's building after building after building of exhaust stacks just dumping pollutants out into the environment. Do you think I'm not breathing that in? I absolutely am, to a certain level. So again, we have to think about throwing this into atmosphere and then the possible reentrainment of these pollutants back into the lab, or their entrainment of these pollutants into other buildings adjacent to the building in which you're throwing these pollutants out of. The carbon impact. One 6-foot ducted fume hood consumes about 22,000 pounds of CO2 a year. One. You have a hood-intensive lab that has 77 hoods, 100 hoods. You can only imagine the impact to the environment. Again, there's a domino effect here. There's a cascade effect of ductless and ducted fume hoods and the value added that ductless filtration brings to your laboratory. Exposure limits are not fully addressed with ducted fume hoods either. And I'm going to touch on that in a moment in my next slide when I talk about, is filtered fume hoods really safe? Is this truly a safe solution? Well, let's look at some of the standards. ANSI Z95, NFPA 45, CSA Z316, and AFNOR NFX 15-11. All of these standards were designed to ensure safety within the laboratory. The most important standard here in regards to filtration is the AFNOR NFX 15-11 standard, and that is an EU-based standard. Now, if you noticed, a lot of these NFPA points to ANSI Z95. ANSI Z95 points to AFNOR NFX 15-11, and that is the game changer. So let's really look at the standards. They are really safe. The standards state that you must have 2 layers of redundant filtration, you must have continuous and automatic detection, and you must have detection accuracy. ANSI states that no greater than 25% of the TLV can be released at the filter's exhaust. Again, NFPA points to ANSI, but more importantly, ANSI actually ultimately points to AFNOR, in which AFNOR states that you never should see release at the filter's exhaust exceeding 1% of the threshold limit value. CSA gets a bit tricky where it's a fraction of the OEL, but ultimately, AFNOR should be the standard in which you look to ensure safety. As far as containment, all the hoods meet containment. ASHRAE 110 standard and AFNOR XP X15 206 standard. So as far as containment and filtration efficiency, we adhere to. In fact, we go above and beyond in some instances. So let's take a little deeper dive into AFNOR to give you a bit of a one-on-one, as it is a EU-based standard. Many of you may not know exactly what it encompasses, but it encompasses the products in its entirety. So a fume hood in its entirety as far as containment efficiency, filtration efficiency, and air phase velocity. It gets much deeper than that. Remember, it is the standard in which we point to for filtration efficiency. So what does that mean? It means that you must have documentation providing a list of chemicals that can be retained by the filtration, not weight by volume, but by the actual filtration. This chemical listing I have here in my hand is a listing comprised of over 750 chemicals in which have been tested under 6 different concentrations twice. It represents thousands of chemicals. We know down to the molecular gram of each one of these chemicals that we can retain before we've seen release detectable no greater than 1% of the threshold limit value. All of this testing is performed in a hermetically sealed chamber, as you see here, so that we can capture release at the source and without any dilution. Because we've done our due diligence in testing these chemicals with our filtration, we're able to provide a certificate of validation of the handlings within the enclosure, essentially a feasibility study. Is filtration the right solution to meet my handling requirements? And if it is, what is the overall longevity of the filter life cycle and the guarantee I'm able to have of these filters? Typically, on average, our filters range on a life cycle anywhere between 24 and 48 months. That is our guarantee throughout that life cycle, again, that we will not see release at the filter's exhaust exceeding 1% of the threshold limit value. We cannot perform this feasibility study without this chemical listing. It is absolutely critical. And then, of course, we have third-party validation and test data. We go a little bit deeper. Next on the next slide, but this just gives you a quick glimpse of what's inside this chemical listing booklet. And of course, you can come by our booth to get further details about this, and we will send you PDFs of this chemical listing as well. But then AFNOR gets a bit deeper. We have to ensure our products perform under 3 operating conditions: normal, detection, and safety. What do they mean? I mentioned normal operating phase earlier. That's at which point we provided you the feasibility study and we determined the filters are going to last 24 months. We have to guarantee that throughout that 24 months, we never see release at the filter's exhaust exceeding 1% of that threshold limit value. Now, let me stop there. The way we configure our filtration columns is very similar to what you see on the screen. Again, you can stop by our booth to get further details. But what you see here is a primary HEPA filter. Now, in this instance, this is because the customer will be handling powders or acids. Or we want to slow down the kinetic energy of that molecule entering the carbon filter. So we have a HEPA filter in some instances. We have a primary carbon filter always. We have a fan module, and then we have a redundancy secondary level of filtration, which is the same filter that we use on the primary level of filters. Sorry about that. If you notice, sandwiched in between the 2 main carbon filters is a fan module. Within this fan module, we have detection sensors, dry contact metal oxide sensors that we code dependent upon the first prominent breakthrough chemical. And that's going to detect any type of breakthrough past this primary stage of filtration. So when there's less residency sites, we may get a spike in concentration. That sensor will indicate that we've seen a spike in concentration, but because we have redundancy level of filtration, even at that detection phase, we still guarantee that they'll never be released exceeding 1% of the threshold limit value. Now, at detection phase, at times we may see a spike in concentration and then it remediates itself. This happens often when we get to detection phase. Once you get to detection phase, you'll see spikes in basically blips in the radar, a parking lot during Christmas time. Cars don't know where to go, they overflow, and they find a new place to park, typically in the medium, but nonetheless, they find a different place to park. Just like the molecules, they can't find a parking spot, they bypass that primary level of filtration, they find a new place to park, and that would be in that secondary level of filtration. We don't want this to occur often because the more you allow detection phase to occur, the less residency sites you now have in that primary level of filtration. And that's important to note because when the filters are replaced, remember, we're saying that the filters last about 24 months. When the filters are replaced, it's only this primary level of filtration that's replaced. This filter gets disposed of. The new primary filter is the secondary that gets rotated down to become the primary, and then the new filter that's ordered becomes the secondary level of filtration. So it's important that we don't allow this hood to get into detection phase, but in the event it does, we have the sensor, we have trigger alerts, we have smart light communication, which will give you a visual, and then we enrich that with our eGuard web-based program where you can actually get real-time data feeds of the performance of the product. So that's detection phase, but then we take this one step further into safety phase. What is safety phase? Safety phase is at which point we've seen detection, we've seen a spike in concentration continuously, and then we've had a spill within that fume hood. This is at which point we guarantee that we still will not see exposure exceeding 50% of the threshold limit value of the cumulative chemicals released at the filter's exhaust. Now, you get to safety phase, you really got to look at your administrative controls because we have belt and suspenders built in to ensure the hood never gets there, as well as employees that constantly monitor our customers' accounts to ensure they're replacing the filters according to lab recommendations. So you really got to look at administrative controls if you get to safety phase. But in the event this does happen, we do have a guarantee that they'll never be released greater than that 50% of the threshold limit value for 1/12 of the filter life cycle. Now, just as much as we know our capabilities, we do also know our limitations. And basically, it's those chemicals which are naturally gaseous under normal temperature and pressure conditions. After that, we have not recommended chemicals. Mercury, hydrogen cyanide, mercury because it's well retained, but we cannot really detect it that well. And because it's extremely toxic, we choose to stay away from mercury. Hydrogen cyanide, because it's immediately lethal. Chloric acid, obviously you need a wash down hood because of the crystallization of the acid. And any type of heavy volumes of acid digestion, not recommended. We can do microwave acid digestion, but if you're doing true acid digestion in baths, really not recommended for ductless fume hoods. So yes, there's still a need for ducted hoods, and both can live together. So let's just talk a little bit about that smart technology I mentioned. And of course, again, stop by our booth and you're going to be able to really get into the details of this technology. But not only are we going to detect for breakthrough in the filter, but we're also going to constantly monitor the ventilation, the air, and the air face velocity. So those three things, the performance criteria, constantly monitored: the filtration efficiency, the mechanical aspect, and the ventilation and face velocity. Not only does this allow you to constantly monitor the hood, but you can actually extrapolate data and information to improve overall laboratory practices. For instance, if you notice that a sash is left open every day at a certain time for a long period of time, you can kind of narrow down who's using that hood and go to that individual and say, listen, I know you're operating the hood during these times, and I'm constantly getting alerts that the sash is left open, or we have a face velocity alarm. Can you show me the process? And when they show you the process, you may realize they're removing or opening the sash. Now you can talk to them about the proper means of using a fume hood and why the sash is important, and why containment is important. So ultimately can help you improve overall laboratory practices, but also this system is constantly monitored to ensure safety is never compromised. So in summary, compliance is not always enough. Our primary focus must always be on safety. Review standards, take samples of your air quality and determine where solutions can be implemented. Where can I add filtration devices? Do I need to add a whole room air filtration system? Do I need to add a containment ventilator enclosure, CVE, over a rotary evaporator or HPLC? Find ways to improve current engineered control systems. And of course, I do want to leave you with this. Safety continues far beyond the lab. While we're always concerned about what's going on inside, sometimes we overlook the outside environment, and we all have to do our part in improving what we do so that we improve our environmental conditions, because it is a very real issue, as many of you are witnessing. So with that, I thank you all for being here. Please join us and visit our booth at booth number 905. Reach out to me if you have any questions. Thank you very much.